Hello, my name is Samuel Remedios, and I'm going to be presenting our work entitled Deep Filter Bank Regression for Super Resolution of Anisotropic MR Brain Images. Clinical MR scans are often 2D acquired with high-resolution 2D in-plane slices, like the one shown on the left, which are stacked to form a volume. However, when this volume is viewed through plane, we can see it is low resolution, such as the image on the right. Furthermore, sometimes these in-plane slices are acquired with slice caps, which further degrades the through-plane resolution. This is a problem for automated neuroimage processing, which generally requires isotropic voxels. To address this, super-resolution methods have been proposed that map low-resolution to high-resolution estimates. Contemporary methods do this with deep neural networks that map a low-resolution image Y directly to their high-resolution estimate X hat. However, these methods do not characterize the missing information necessary to do this. Instead, it has to learn it implicitly by viewing lots of data. And also, these can be sensitive to domain shift that require lots of external training data. Our contribution is twofold. We present an augmented novel observation model, and then we present a super-resolution algorithm that takes explicit advantage of this novel observation model. Furthermore, we do this with internal training. We require no external training data, and therefore we are not sensitive to intensity domain shift. So shown here is the classic observation model. Our low-resolution image Y, shown on the right, is obtained by filtering and downsampling a high-resolution image X. One of our contributions is that we notice that this is part of an M-channel perfect reconstruction filter bank, shown here, which states that if we have the correct filters, H0 through Hm-1 and F0 through Fm-1, we can decompose our high-resolution image X into different subbands, one of which is our observed low-resolution image, and the rest are detail coefficients, D1 through Dm-1, which are then upsampled, filtered again for interpolation, and then added. And if these are the correct filters, we actually perfectly recover our high-resolution image. So our job is we need to find out the detail coefficients, and we need to find out the missing filters for the encoding and decoding filter banks. We do this in two stages. In the first stage, we learn and approximate this perfect reconstruction filter bank. What we do is we sample in-plane patches, high-resolution in-plane patches from the volume, and we send them through this filter bank, through our initialized filters. We then calculate a reconstruction error and backpropagate because the whole filter bank is differentiable. And what we can do is we can update the missing filters from the perfect reconstruction filter bank with gradient descent. We repeat this iteratively until convergence. In stage 2, given that we have an approximate perfect reconstruction filter bank, we now want to learn a mapping from the low resolution image we have to the detail coefficients. Here's why. In order to actually perform super resolution here, we only have the low resolution image and the filter banks that we approximated. And in order to recover this high resolution image, we need to estimate these detail coefficients. We propose to do this with a deep neural network right here, and we actually use a pix-to-pix style GAN to learn this mapping. Here we're going to show some of our results, but first the low resolution image is shown on the left and the high resolution ground truth is shown on the right. And here are the Fourier domain for reference. This is 6 times low resolution, by the way. So here's a B-spline interpolation, which of course does not add high frequency information. SMORE is a competitive internally trained super resolution method for anisotropic volumes, and here's our approach. We can see that we recover more high frequency information, which makes sense because we're explicitly aiming to do so, and this is reflected in different regions in the image where we get sharper edges and better defined images. Quantitatively, we evaluate with PSNR and SSIM, and we can see that as the resolution worsens and the gap gets further, our method better performs compared to the competitors. In conclusion, we've presented a novel observation model which hopefully will provide a new theoretic basis for super resolution. We also show a new super resolution algorithm that regresses that missing information directly. And we've shown that as the resolution worsens, our method outperforms the competitive approach. So please come see the poster session on Tuesday, September 20th. We're poster T82 for more details. And you can also check out our paper by clicking or viewing the QR code here. Thank you.